So this is a problem on analysis of beam. We'll analyze this beam by direct stiffness method. So this is a beam what has been given here, two span continuous beam. At end A it is fixed, and the support at B and C are hinged over here. The I values have been mentioned in this uh, particular figure. Span AB, for span AB it is EI, whereas for span BC it is 2EI. Okay, now we'll divide this beam into two members. Span AB will be taken as one member and span BC will be considered as another member. So in case of beam, each member will have 6 degrees of freedom. So for span AB and span BC, the degrees of freedom have been shown over here. Totally overall, if you look at the degree of freedom, it will be 2. There will be 2 unknown displacement, rotation at B and rotation at C. But when we are dealing with the direct stiffness method, we'll treat each member separately with its own degrees of freedom, elemental degrees of freedom here. So these are the degrees of freedom for any beam element. So you'll have axial deformation, translation, as well as rotation at each end, two ends. So you'll have come across 6 degrees of freedom totally. The same have been shown for this AB and BC. So now we'll develop the stiffness matrix with the help of these assigned coordinates. The numbering of coordinates, I told it is left to you. You can choose conveniently what should be the numbers to the given to the coordinates, and even the directions, whether it should be towards right, left, upwards, downwards, clockwise, anti-clockwise. That can be assigned as per the user's choice. Now coming to this problem, so let us start with developing the stiffness matrix for each of these members. And this is the stiffness matrix for beam element, what will be given here. This doesn't require any transformation, or we don't need to use the rotation matrix in this case, because all our members are parallel to the global x-axis. In such case, you don't have to go for any transformation of this stiffness matrix. Whatever we develop here, it will be with respect to global coordinates. So the element of a beam, okay, so we can express its stiffnesses, axial stiffness, translational stiffness, rotational stiffness have been taken in this particular matrix over here. When I try applying this matrix for members, each of the members, then I'll be able to write the element stiffness matrix for the two members, that is for member AB and member BC. So when I take the first member, that is the member AB, the member AB has been given member number 1 or element number 1, member BC has been given element number 2. So these are the number given for the elements, these are the numbers given for the coordinates. Coordinates are numbered within these circles, okay, so they indicate that coordinate numbers, circled numbers, whereas these indicate the member numbers. Okay, these nodes are nothing but the joints, node 1, node 2, node 3, what we has been mentioned here, they are just the joints over there. We call them as nodes for that is the uh, terminology what is used normally. Okay, so if I take the first member, that is AB, the length is 4 meter, I, moment of inertia is I, A and E will be constant for the entire beam. So material Young's modulus is constant, and the cross-sectional area is taken to be constant here, since nothing has been told about cross-sectional area over here. So A will not come in picture, and we are not interested in axial deformations also even in this case. So if I is varying, it indicates area is also changing over there, or there may be a change in the area, but we'll be considering the area to be constant in this case. Okay, so E by L for member number 1, that will be E is taken outside, which is constant here. So these coefficients will be either in terms of A or I here. So A by 4, that will be 0.25 over here, then 0 0, here it is minus A by L minus 0.25 0 0. Okay, then coming to the second this one, 0 12 EI by L cube, so this is 12 EI by L cube here. Okay, 6 EI by L square 0.375, it comes out as 0.375, and minus 12 EI by L cube, so and 6 EI by L square. So this calculation is done keeping in mind this matrix what we obtained earlier for a beam member, okay, or for a member of a rigid jointed frame. This is what is the matrix, element stiffness matrix. Okay, so this will be giving us the element stiffness matrix in global coordinates for beam whenever the member is parallel to our global x-axis. In that case, this directly gives you the element stiffness matrix in global coordinates over there. In case if it is not parallel, then we have to go for transforming that coordinates from local to global. So here we don't come across that case, and go on substituting the values of these I, A in this matrix, and what we'll be able to do is we'll be able to get the element stiffness matrix for this first element K1. Okay, so 3 plus 3, 6 degrees of freedom, so we have a matrix of 6 by 6 over here. So this will be the element stiffness matrix for first member. Similarly, the element stiffness matrix for the second member, when I take that member BC, I have span of that member or length of the member as 6 meter, and moment of inertia is 2I. A and E are considered to be constant. So K2 now becomes the same matrix what is here has been used in developing the element stiffness matrix for the second member also. So AE by L, okay, E has been taken outside, A by 6, okay, that comes out as 0.167 A minus A by L minus A by 6, so minus 0.167 times A. Rest other terms here are 0. 12 EI by L cube, so 12 into 2I divided by 6 cube, that comes out as 0.11. 6 EI by L square, so 6 EI by L square, this one 6 into 2I by L square, 0.33 times I. Similarly, the other coefficients have been obtained by substituting the appropriate values of I or L or A. Okay, so this gives us the element stiffness matrix for the two elements. Now we have taken care that the coordinates. Okay, so first element what it is having is coordinates 1 to 6. Okay, coordinate number 1 corresponding to axial deformation, 2 translation at joint 1, 3 rotation at joint 1. Similarly, 4 corresponds to axial deformation at joint 2, 5 translation at joint 5, joint 2, 6 rotation at joint 2. Okay, so these numbers in red, they indicate what coordinates are there in member number 1. Okay, so accordingly the stiffness coefficients will be developed. So member number 1, coordinate number 1, what we have is axial coordinate. Okay, so it will be stiffness related to axial deformation, E by L. Similarly, the second coordinate, member 1 coordinate 2 corresponds to translation, so this coefficient is translational coefficient, 12 EI by L cube. So it is very much important that you mark these coordinates while developing the stiffness matrix. This will help us in assembling the global stiffness matrix for the entire beam. Okay, so second element what we have is we come across the coordinates from 4 to 9. So 4, 5, 6, 7, 8, 9, 4, 5, 6, 7, 8, 9. 4 and 7 for axial stiffnesses, 5 and 8 for translational stiffness, 6 and 9 for the rotational stiffness over here. So these are the coordinates. Now once we have developed the element stiffness matrix in global coordinate, now we will be assembling these two matrix so that we will get the stiffness matrix for the entire beam. So this is the stiffness matrix for our entire beam here. Okay, so two elements, 9 degrees of freedom, this will be having a size of 9 by 9. This is the element. Now how you are going to assemble this is, consider this, say I want to write this first element of the global stiffness matrix. Okay, so what I have is K11. Okay, K11, so it will be a force in the first coordinate due to unit displacement in first coordinate. So where is K11 in these two? You need to search for that. In my first member I come across K11 equal to 0.25a. In the second member I don't get this K11 because that coordinate 1 is not coming in the second member over here. There is no coordinate 1 in this second member. There is a coordinate 1 only in the first member. So K11 will be simply 0.25a. K22 similarly, this is related to only first member, coordinate 2. So it will be simply 0.187 times I. Okay, like that we need to look for the coordinates in the both the members. Okay, any coordinate which is shared by both the members, you need to consider the stiffness coefficient in both of them and add them together. Say for example this 4 4 K44. In the first member, I have the fourth coordinate here, axial coordinate, whereas in the second member also I have this fourth coordinate. So in case of first member, what I have is 0.25a. K44 is 0.25a for first member. Similarly, for the second member, K44 is 0.167a. So here, while writing this K44 for entire global matrix, I'll be adding these two values, 0.25a plus 0.167a. It comes out as 0.417a. Okay, so like that, if I come take up this K5, say 5 5. Okay, here it is 0.1875. Here K55 value is 0.11 times I. So 0.1 minus sorry 0.1875 I plus 0.11 I. So 5 here it will come out as 0.297. Add them together, it will give you 0.297 times I. So this is what is taken care while writing the elements in this entire matrix, entire global matrix for the beam. Okay, so it will be a matrix of size 9 by 9 over here. So you can check other elements also here. 1 6, it comes only in this first one. Okay, in second there is no coordinate 1. Coordinate 1 is not coming in this second matrix over here. So 1 6, it will be simply 0. Value will be taken only from this K1 matrix, whereas in some cases the values will be taken from both K1 and K2 and they will be added together and they will be substituted here in the entire K matrix over here. Okay, so this is what we have for the global stiffness matrix. It is of size 9 by 9. Okay, now coming to the our beam. Now what we have is, look at the support conditions in our beam. At the first joint, it was a fixed support. So in this case, if you look at this beam again, so fixed support is provided at A at joint 1. There is a hinge support at B and hinge support at C. So here no displacements are allowed at joint A. At B only rotation is allowed and at C only rotation is allowed. Okay, other than these there is no displacement which have been allowed. And also in beam we are not interested in axial deformation. Beams, they are axially very rigid, so very little amount of deformation may be present or there it may be zero. Even if it is present, it is very small. The axial rigidity of the beams will be very high or they will be very stiff. They don't allow any axial deformation. So that for that purpose we are, even that axial displacement can be neglected over here. And now we'll come to this global stiffness matrix of the beam K. So when that three displacements have been arrested at joint 1 or at end A, so I have to delete first row, column, second row, second column, third row, third column. So all these elements will be gone. Since no displacements are allowed over there, we are not interested in these stiffnesses also. So these are gone. Now at joint 2, what we have is 5 4 5 6. These are the coordinate. Only displacement in sixth coordinate is allowed, that is rotation in sixth coordinate is allowed. So I'll retain only the row and column corresponding to this rotation, that is sixth row sixth column will be retained. Other than that, rest other will be deleted. So these we have already deleted. First row has been deleted, so this value is gone. Second row deleted, this value is gone. Third row deleted, this is gone. Okay, fourth coordinate axial deformation, we are not interested, delete this also. Okay, fifth, here it is a roller support, so this vertical displacement of the joint is not allowed, so delete this row and also the fifth column also. So these values have been deleted. Now sixth row, sixth column will be retained. Okay, in that we only come across 6 over here. Okay, so this will be the value what will be existing over there. Also in the second member, what we have is 4 5 6. In this only sixth degree of freedom is present. Degree of freedom in sixth coordinate is allowed, so that has been retained here. 4 and 5 we are already deleted when we considered the first member. Now coming to the next joint, that is at joint C. Here 7 and 8. 7 we are not interested in axial deformation, it will be negligibly small. So seventh row and column values will be deleted over here. Similarly, eighth, there will not be any displacement in the vertical direction of that because of that support. So this eighth row and eighth column will be deleted. Ninth coordinate corresponds to rotation. Yes, rotation is allowed at that joint C. So we are going to retain the values of 9 9. So only values that will be retained here is the rotational coefficients of the stiffness coefficients have been retained. So 9 6 and 9, these are the degrees of freedom that will exist. 6 9. Okay, 6 9 6 6 6 9 9 6 9 9. These values will come in our global stiffness matrix. So this entire 9 by 9 matrix just reduces to a matrix of 2 by 2, because global degree of freedom here is 2. What we have is 2 degrees of freedom over here, theta b theta c. 2 degrees of freedom, rotation at b, rotation at c, theta b theta c. So the once we assembled that, now we are eliminating those rows and columns where displacement have been arrested. So this finally has reduced to a matrix of 2 by 2 over here. Okay, now calculation of nodal forces. Whether are there any forces which are directly applied in the coordinates? No, we don't have any such forces which are directly acting in the coordinate in the beam. So that matrix P matrix will be 0. Whereas the forces which are arising in the coordinates due to the loads applied over the member, they exist. Now for that you find the fixed end moments in member AB and BC, then see what will be the net force in the second this coordinate number 6 and coordinate number 9. Okay, so in coordinate number 6, mfba plus mfbc, that will be the net force over here. In coordinate number 9, mfcb will be the net force that will be applied. Okay, so I have this force matrix. One of the force matrix, that is P matrix, is 0 because no forces are directly applied in the coordinate. There are no couples which are applied in coordinate 6 or coordinate 9, so that will be remaining 0. This matrix will be 0. So the PL matrix, this comes from calculating the fixed end moments and then finding what is the net force which is there in the coordinate over here, that is in coordinate 6 and in coordinate 9. Okay, so once we have this forces PL matrix, then we'll apply the condition of equilibrium. P is equal to K into delta plus PL. Okay, net force in any coordinate will be equal to the forces arising due to displacement plus the forces due to the applied loads on the member. On solving this, we'll come to know the unknown displacement what are there. Okay, so theta B 15.96 over EI and theta C minus 30.59 over EI. Knowing this theta B and theta C, we can now go for finding the moments by applying the slope deflection equation. So use these values of theta B, theta C in the slope deflection equation, and we can get the movements at supports. Okay, then later we can go draw the bending moment diagram over there by normal method what we used to follow earlier. Okay.